This is going to be mechanics, grade 11, and this is session 2, where we're going to be looking at components of vectors. The last time the last session, we were looking at basically the simple part of this. Now we're going to be breaking it down into various components. Now, what do I mean by components? Let's just, once again, let's just look at it from the point of view of the practicality. Let's just leave the maths for a moment and everybody's laws and everything else. Let's think about our soap on a rope again, shall we? If I'm pulling this way, it's going to move that way. If I'm pulling up, it's going to move up. Well, what happens if I'm pulling a little bit up and a little bit to the right? Obviously, it's going to want to lift and move, isn't it? It's effectively, there's a little bit of the force tending to lift it and a little bit doing this. So there's a force pulling up and a force pulling that way. Can you see that if we had it just like that, all we're doing is we're pulling horizontally. There's no element lifting it up. If I'm going fully up, the only force is up. This way, there's an amount pulling up and there's an amount of force pulling that way. This is called the horizontal component and this is the vertical component. Essentially, what it is it's going to be a trig relationship between the two. Let's just put that back to black pen. And now let's just have a look at what we've got. Let us say, for example, we have got a force acting in that direction, which is what we were looking at over here with this string, isn't it? Let us say that that force there, F, is going to be 100 newtons. Now we need to say, remember, part of that force is going up and part of that force is going along that way. And the last bit of information that we need, obviously, is we need to know what the angle theta is there. And let us say for this case, hang on, let's call it 30 degrees, shall we? Because I'm going to do one at 45 and one at 60, just to show how this is going to change. Now, if we remember, we said, and I said in the last session, stand at the angle and look out. Find opposite. It sounds very silly, but you'll find that if you do that with physics and if you do that in maths, it makes it a lot easier because these triangles are going to turn around. They're not always going to be nice and nice and shaped like that one. They're going to go in different directions. So what do we do here? We say, right, I have located opposite, then this one we know from trig is adjacent, that one we know is the hypotenuse. So let's just take a look and say, okay, but hang on, sine of theta is going to be, by definition, opposite over hypotenuse, which is going to be opposite over 100 in this case. And sine of theta is going to be equal to the sine of 30 degrees, isn't it? Now, if I rearrange, it means that the opposite side, and you've done this with some of the trig triangles really, the opposite side is going to be equal to 100 times sine of 30 degrees. 100 times sine of 30 degrees is going to be equal to 50. Now I can go and say, then this over here, this is 50 newtons. What if we do with the cos? Same thing, we say, right, cos of theta is going to be equal to adjacent over hypotenuse, right, which is going to be A over 100 is going to be equal to cos of 30 degrees. Therefore, A is going to be 100 times cos of 30 degrees. And if we work that out, we get 100 cos 30 is going to be equal to 86.6 newtons. Now we can go back to our diagram, and we can say this is going to be 86.6 newtons. This one here you can see is in the y direction, isn't it? We call this one Fy. This is in the x, this is Fx. Fy and Fx are called the horizontal and vertical components. In other words, what is a component? A component on a bicycle or a car is something that fits into it. So a component could be a carburetor. Don't know if they still have carburetors. Or a fuel injection thing. Or a component is actually a wheel is a component. It's a part of. So what it means is that these components, the horizontal component and the vertical component, are the two other parts of that vector, which is our hypotenuse. I think that's not really a difficult concept to grasp. Why are we doing this? Well, remember in the previous session we said we look vertical and we look horizontal. When we look vertical, we look and see, is up more than down, or is down more than up, or are they equal? We look horizontal, right more than left, left more than right, then are they equal? If they're equal this way and equal this way, I'm in equilibrium. If there's an imbalance, we're going to move. This is now so that we can deal with forces that are acting at angles. Because obviously there's going to be situations where not everything is pulling straight this way or lifting straight up like that. There's going to be a situation where a force is applied at an angle. Just while we're talking about forces, please remember that if I am pulling, that is the same as a push. So therefore, I could pull something or push something. As long as I'm pushing in this line and pulling in that line, it's the same kind of thing. All right? And one last thing is when we look at a piece of string, they will say, calculate whatever. We always refer to the force in a piece of string as a tension. When we pull it, it goes to tension. If we try and push a string, it just goes flop in the middle, doesn't it? So the tension is the pull in the string. So let us now I want to just move my screen up slightly. You can see that we've got here a 50 and an 86.6. If you remember back to the previous session, what did we do? We took two forces, which was a force in this and this direction, and we added them together using the vector method. In other words, we used Pythagoras. We said 86.6 squared plus 50 squared, and we took the square root. Now, if we did that, we'd get back to the same. So what have we done? Is we've actually done the exact opposite of what we had last time. Last time we found out the force this way and the force this way, and we added them to get the hypotenuse by using Pythagoras, and we worked out an angle. This is exactly the opposite. So before we constructed the resultant, now we're taking a force and we are deconstructing it into a horizontal and a vertical component. That's in essence what we're going to do every time that we see a force which is acting at an angle. That's very, very important. Let us look, for example, let us take this example here that I was looking at a little bit earlier. Let's say we've got a situation like this. And I'm sure you've seen this one in your books, if you've probably even done it as a homework exercise, or one very similar to it. Let us say we've got a force acting that way, and let's call it of 50 newtons, right? And we have a force acting this way of, let's say, 40 newtons, and they tell us that that's at an angle of 45 degrees, and that's at an angle of 30 degrees. And let's look at a force acting down of, let's say, 70 newtons. Okay? And they say to us, calculate the resultant force. Okay. Now, obviously, if they are saying calculate the resultant force, that thing is not in equilibrium. It's going to move. How do we do it? The first thing we do is we recognize immediately that we have got forces in directions that are not vertical and horizontal. So the first thing is we break them into the vertical and horizontal components. Now, there's no reason why you couldn't do this on the side of your worksheet if you wanted to. Take each one and break it down separately. Let's take this one. What have we got here? What did we say? We stand at the angle and look out and locate opposite. Why? Because opposite is the one that's going to go with sine, isn't it? So this is my opposite. So this one is going to be 50 times sine of 45 degrees. This one then must be 50 times cos of 45 degrees. Always do sine before cos, right? Cos z as opposed to s. So let's just standardize on doing that. Then we can do the same here. I'll just change it for color here. Let's go to blue. Okay, there's a component, and there's a component, and there's our angle of 30. I stand at the angle and I look out, and what do I see? I see my opposite there. Opposite is going to be 40 times sine of 30 degrees. This one's going to be 40 times cos of 30 degrees. Let's just make that look a little neater like that. Then we'll go and use our calculator and let's work them out and see what we get. Right? Let's take 50 times cos of 45, 50 times cos 45 is going to be equal to 35.36 actually newtons. Right? 50 times sine 45 is going to be equal to 35.36. It must be, because it's a 45. That must be equal to that. Right? So now what have we got? Let's look at the other side. 40 times sine 30. 40 sine 30 is going to be equal to 20 newtons. And 40 times cos 30. Cos 30 is going to be equal to 34.64. That one. Right? Now we can say, right, let us have a look horizontally first. So we now say, right, horizontal direction. We've got, let's do the drawing, 35.36, and this way 34.64. So you can see that there's a little bit of force. It's not totally balanced in that direction. It's very close, but it's not. What have we got? Do we have a resultant force in this direction? Yes, we do. It's going to be a small force acting that way of 35.36 pull that way minus 34.64. Is 0.72. Right? Now let's have a look in the vertical direction. What is pulling up? Can you see we've got 35.36 and we've got 20. So let's put them in. 20 newtons, and there's our 35.36 newtons. And pulling down, we've got a total of 70 newtons. Let's have a look if there's a greater up or a greater down. Let's see. 70 is going down. Minus 20 minus 35.36 is yes. I've got 14.64 newtons acting down, haven't I? I'm just going to change them to a red force. So my downward force is going to be 14.64 newtons, and my resultant in the horizontal direction is 0.72. So what have we got in all of this? We've got a little force of 0.72 newtons that way, and we've got sorry, that was not very neat. Let me just change it. And 14.64 acting down. What do? We do that, and we work out the resultant again. Just change the color so that it's a little more. There we go. And what do we say? We say that in this case, the resultant is going to be equal to 0.72 squared plus 14.64, 0.72 squared plus 14.64 squared, all to the power of a half. Right, and we're going to do that. 14.64 squared is that, plus 0.72 squared equals that, and to the power of a half is going to be 14.66. It's obviously because that's very small, and then we go and we say what is angle theta there, and we say theta is going to be equal to arctangent of 14,64 divided by 0,72, and we work that out, and we say it's going to be 14% divide 14.64 divide 0.72 is that 61 over 3. It's obviously going to be very, very close to it's going to be 87.2 degrees. Right. So let's now say what is actually happening here. It means that there is a resultant, which means this thing is going to tend to want to move, and it's going to want to move almost vertically down. It's going to be going down at 87 degrees, and it's got a resultant of 14.66 newtons. Right? So in this particular case, we didn't have an equilibrium. Let us look at a case where they give us, let us say, this. Okay. Let us say they give us a situation where they tell us that, I don't know, let's draw something here. Right. Make sure it's black. Let's say they say there's a piece of string over there. Hanging on there is a weight of, I just generally use 10 kilograms, just for whatever. All right? They tell us that there's a string holding it up there, and this is 30 degrees. Oh, what I forgot to say is in physics, the key, one of the keys is do a drawing, because we're going to start looking at dynamics where things start moving. And when they start moving, we need to do a drawing before they start and after they've finished the movement. It's very key to understanding concepts in the future, but it also puts it out logically. You cannot visualize from a word problem what is actually happening in front of you. So when we do things like projectile motion, which is a great way of saying throwing things up and watching them come down, or dropping them and watching them come down, we need to be able to say, where are we, what are we doing, and we put in what we've got. Same with this, right? So the drawing is absolutely critical with physics. 30 degrees, and they say to us, right, in this over here, I have got a force of, okay, this I put in always Fw first. Fw here is going to be 9.8 times 10, which is giving us our 98 newtons, right? So we've got 98 newtons down there. And they say to us we've got a tension there. And in this one, they say they measure in there, all right? Well, no, let's say they say to us, right, what is the tension in that going to be? Right? Let us have a look what we first of all do. First, we put in the weight. And they've told us this is in equilibrium. Next question. There's now not going to be a resultant, is there? Because it's not moving. So we say, therefore, no resultant. There can't be equilibrium. I'm not moving anywhere. I'm not going up or down. I'm not going left or right. Okay? And we first of all say, right, we've got a force at an angle. So first step is we're going to go and we're going to put that force into components, right? Now, we haven't got a number yet. Don't worry about that. Just follow the same rules and the same recipe over and over again. Do it in components. Opposite is t sine. So what is this one? This is t sine of 30 degrees. This is t cos of 30 degrees, right? Now let's see what is t sine 30. Well, it's going to be sine of 30 is going to be a half. So this is going to be 0.5 times t. This one is going to be cos 30. Is that, okay, is 0.866 times t. Right? Now, they tell us it's in equilibrium. So what are they saying? They are saying that the total forces up must equal down, and the forces to the right must equal the forces to the left. That's what we're saying. Now let's have a look. What are our forces up? Now let's introduce the sign. Let us just say going up is positive and down is negative. Upwards positive, down is negative. So upwards here, we've got a force of 0.5t. Down, 98 newtons. To the right, we've got 0.866t. And to the left, we don't know. So let's call it T2. Right? So what do we do next? Now we go and solve it. Okay? Which is this. We say, okay, put it back. Let's just look. 0.5, let's go vertical. 0.5 times t, the vertical one, must be equal to 98 newtons, which is the down. So what is t? Well, t is going to be 98 divided by 0.5. And let's just do that. 98 divided 0.5 is going to be 196 newtons. Now, hold on. Now we know t. So we say, right, therefore, T2 must be equal to 0.866 times t, correct? Because let's just scroll it back and have a look. Can you see there? The T2 must be equal to 0.866 times the t. Now we can work out what T2 is going to be. T2 is going to be 0.866 times that, which is going to be equal to 0.866 times 196, which is going to be times 0.866, which is going to be equal to 169.7. So therefore, the tension in the horizontal string in our diagram was equal to 169.7. Very often, they will say to you that the maximum force that it can withstand before it breaks or before it comes loose from the wall is 170 newtons. Will it break or will it come loose from the wall? The answer is no. Why is the answer no? Because the force in there is now 169.7. It's less than the 170 newtons. It's very close, granted. So it's going to be maybe, maybe not. But it is theoretically, it's less. Therefore, it was not going to break, or it's not going to pull out from the wall. The next session that we're going to do is we're going to take this study just a little bit further into another type of problem where we're going to do two simultaneous linear equations. Pretty much about the limit of what you get, okay, in order to solve. And then we're going to start looking at the concept of no more equilibrium. We're going to start looking at things moving. So we're going to start looking into Newton's equations. So we'll do an example or two, and then we'll move it along into some other concepts where we'll talk about Newton's equation. And what we'll do is we'll then lay out the Newton's equations, we'll examine them, and then we'll start applying them onto relevant concepts. I also need to go back in the other one, and I need to go and do the one where I said I was going to do it at 35 degrees, etc., etc. I didn't do that, the first problem that I had up there. And what we're going to see is we're going to see how the vertical component gets more and more and more. As this angle lifts and lifts and lifts, the vertical eventually becomes equal to the force itself, and the horizontal gets less and less. But we'll consider that one in the next.